C, called the C opportunities for this webinar series. And we are now heading to the second part 2 on offshore wind power efforts and challenges. I'm Benjamin Belwald, working at Volcanic Phase and Petroleum Research in Oslo. And I'm together with Carla Martin-Clavé, who organized this event. And we're guiding you through the talks and the discussion afterwards. So this is the program for tonight. So I give a short introduction on the special interest community on decarbonization and energy transition. And afterwards, we're going to have 2 exciting talks. The first one by Equinor. Gertrud Hausken will speak about the Hiven Windpark project. And afterwards, Martin Vanneste from NGI will give a presentation on data-driven ground models for offshore wind development. And in the end, we will have a Q&A, so questions and answers, which you're kindly asked to already write down in the chat during the talks. I would also like to thank all the participants who helped promoting and organizing this event, so EAGE in general, but also special thanks to the local chapters, local chapter Aberdeen with the help of Paul Mitchell, then local chapter London, Artem Kachubin. From the Netherlands, we have Diego Rovetta, here in Oslo, or from Oslo, the Artem Kotonev, and also the Society of Exploration Geoscientists of Oslo by Luke Griffiths. So big thanks to all of you, and I think it's a great initiative that these local chapters work together and promote such activities. Good. So this event is part of an event organized by the EAGE Special Interest Community on Decarbonization and Energy Transition. It has had its origin at or launch session during the EAGE 2019 in London, and the aim is to promote knowledge and development skills among geoscientists and engineers, which work on decarbonization and this energy transition topics and technologies in aspects covering both surface and subsurface decarbonization, and of course including CO2 sequestration and the advancement of renewables such as geothermal energy, as well as in the wind energy as well. So we have quite an active LinkedIn group, and hope that whoever is not following us at the moment, that you will follow us in future. So please check on LinkedIn this EAGE Decarbonization and Energy Transition Community. There is quite recent updates, and also recordings such as this webinar will be uploaded on this page later on. If you have questions to the events, you can contact our president. It's Karin de Borst from Shell, or also Carla and me. We're both very up to answer or deal with questions or future events. So please join us on this adventure. We're excited in getting the community growing in future. So past events that we organized was first of all this energy transitions in DEWIR. It was supposed to happen in Amsterdam at the annual meeting this year, but then we had a webinar in June, which all of the presenters got a chance to have a special webinar, presenting in a special webinar there. Then we had some local chapters organized a series of talents and competencies in the energy sector. And 2 weeks ago, we had this energy transition in the North Sea, the first part on the carbon capture and storage. Future events that are organized by this community are this GET 2020. So it's the first Geoscience and Engineering in Energy Transition conference. Unluckily, it's online as well. It was supposed to be in Strasbourg. If you're interested, please check this webpage, and you still have a bit of time to register online for this conference, 25th of October. So this week, you still have a chance to register for it. Please check the program. It looks quite exciting. And then EAGE is also organizing this fractured geothermal reservoir webinar. So where you learn more about the characterizing and modeling fractures with limited data sets. That's going to happen on the 9th of November, and please also check the EAGE webpage if you want more information on this event here. So, but today we're gonna talk about wind energy. So we're gonna have a first talk focusing more on the actual wind farm, and then afterwards more on the geological presentation, dealing with geotechnics, geophysics on the seabed and shallow subsurface. What I just would like to show you quickly is that if we think about decarbonization, we're thinking about this CO2 emissions. And there was just in October now a paper out in Nature Communications by Liu et al. Who looked a bit on what's now the consequence of CO2 emissions related to the COVID-19 pandemic. So it looks a bit. We're decreasing the emissions this year. It's different sectors which have less emissions. However, it's assumed that there will be a rebound, which kind of could compensate a lot of what we saved this year. So although we measure less this year, it's the trends could be different. On the figure here down to the right, you see that also this year we have around 1.6 gigatons less of annual change of CO2 emission. That's the biggest change in the last 100 years. We had some bigger ones also related to World War II or the oil shock, but this one is quite drastic, and COVID-19 definitely had an effect, a short-term effect on the emissions at least. If we now speak more on the offshore wind power and the potential, and tonight the session will focus on the North Sea. We see that these areas, they're perfectly suited for offshore wind. You see to the left here the wind speed in meter per second, and the areas here in the North Sea. Once it's a good sign to be in a windy environment. So for wind power, actually, it's a really good setting here. The exponential numbers, we're getting more and more used to that, and they do not always have to be bad. So obviously in case of the wind power now, we see here to the left on the figure, we see an cumulative capacity in gigawatts. And you see since 1996, in this case, the cumulative capacity is growing. And I don't know, maybe the speakers will say something about the future, how they expect this to evolve. For us as geologists, of course, it's important to think about these different solutions that wind power offers. So we have land-based, which we will not discuss today. But for shallow water, depending on the water depth and the sea floor, there is different type of anchoring and technologies involved. And I'm sure that these aspects will get discussed in the following talks. So then I don't want to get this introduction any longer, and we'll now invite Gertrud Hausken to share her screen and give her presentation. I give a short introduction on you while you share the screen now. So Gertrud Hausken got a master degree in science from the Norwegian University of Science and Technology, NTNU in Trondheim. She graduated in physics and mathematics in 1997. And then Gertrud has been working for Statoil, which is now called Equinor, for 23 years within different projects. She started off within the offshore wind pipeline commissioning, flow assurance, and thereafter various positions within interdiscipline management. Gertrud moved from oil and gas projects to the green technologies, and she has been working for a few years with carbon capture and storage projects, and for the last 2 years as a technical manager for the Tampen Hiven project. So I'm looking forward to the presentation of you, and please start. At the moment, we cannot hear you yet.
Unmute me. Does it work now?
Yes, it works now, yeah, perfect.
Can you also see my presentation?
Yes, we can see that.
Good start. Okay, thank you for having me to have this presentation. As you just introduced me, I'm technical manager of the Hiven Windpark project. Just some words on that. Hiven Windpark, it is a new development where floating wind turbines provide power to producing oil and gas platforms. And Hiven is the Equinor patented technology for floating wind. Tampen is the area that we chose for the development, and more specifically, for those of you know in Tampen area, Snorre and Gullfaks clusters. When we presented the Hiven Tampen idea to our partners in Gullfaks and Snorre 2.5 years ago, January 2018, we were very uncertain on how they would respond to this. Well, they responded by the most obvious questions. Why should we do this? And I guess quite a few of you may be wondering as well. But through the project maturation and collaboration with our partners and key stakeholders, we were able to conclude and agree on the concept and development plan from both Snorre and Gullfaks. And this was in the beginning of October 2019, so it's only 1 year ago. So my presentation, it will summarize why we are doing this, what we are planning to achieve, how we plan to do it, and conclude with a short status on where we are today. So on courtesy to our partners on the Snorre field and the Snorre license, we have Petoro, OMV, DEA, Vår Energi, and Idemitsu, who's with us as partners, whereas on the Gullfaks license, we have Petoro and OMV. So before I continue, I would like to run a small video for you. Perhaps that is better if you run it. Shall I stop sharing?
I will do the video for you, that's fine. Can you see it? Can you see the start? Okay, perfect. Then we run it. Just let me know if the sound is not working afterwards.
Det startet med en flytende vindturbin utenfor Karmøy. I 2017 startet driften på verdens første flytende vindpark utenfor Skottland. Høsten 2020 starter vi sammen med våre partnere byggingen av Hiven Tampen, som skal forsyne Tampenfeltet med fornybar strøm. Den vil bli verdens største flytende vindpark. Hiven Tampen-prosjektet vil bidra til videre utvikling av flytende havvindteknologi og redusere kostnadene ved fremtidige havvindparker.
Vi ser jo det her som en god investering for ikke bare Enova, altså det her er jo for nasjonen Norge, fordi at det er med å bringe en teknologi videre som vi har stor tro på at vi kan tjene på i fremtiden. Vi kan tjene på den fordi at det kan være et springbrett for olje- og gassindustrien og leverandørindustrien i Norge inn i nye markeder. Men på lang sikt så besitter jo også Norge noen fantastiske vindressurser, så bare teknologien blir billig og god nok, så har vi også muligheter til å tjene på krafta en gang i fremtiden.
Betongkonstruksjonen skal bygges av kverner på Stord og Dommersnes, før de slippes til Wergeland base i Gulen for montering. I 2022 starter vi sammenstillingen av de 11 vindturbinene.
Hiven Tampen er et stort og komplekst offshore-prosjekt som vi i Equinor har stor kompetanse og lang erfaring på å levere. Sikkerhet er prioritet nummer 1, og vi i Hiven Tampen har fokusert på sikkerhet fra første dag for å unngå å få hendelser i prosjektet.
En etter en skal vindturbinene slepes ut til Tampenfeltet, som ligger ca. 140 km fra land. Når turbinene er på Tampenfeltet, vil de bli forankret opp. Kablene skal så legges for å koble de sammen og knyttes opp til plattformene Snorre og Gullfaks. Vindparken skal styres fra kontrollrommet til Equinor på Sandsli. Vindkraftprognosene sendes kontinuerlig til plattformene, slik at de kan utnytte det fulle potensialet til vindkraften. Dette vil redusere utslippene av CO2 tilsvarende rundt 100 000 biler. Sammen skaper vi et nytt norsk industrieventyr i et lavutslippssamfunn.
Okay, I stop sharing, then you can again go on with the rest of the presentation.
Yeah, thank you. You can see it now. Back again.
Yeah.
Yes. So, just to go back a little bit to the fact why we are doing the Hiven development. It will reduce the emissions of CO2 and NOx, it's the obvious one. It should be noted that there are no requirements for the electrification of either Snorre and Gullfaks though, but it will, Hiven we are contributing to the Norwegian continental shelf and the concrete climate ambitions with a cost-effective CO2 abatement option. The abatement cost is effective given the support regime that is available from Enova that was talking on the video and the NOx fund. And the project does not meet the normal profitability requirements, and the support that we have received from Enova is resulting in an NPV for zero for us, net present value. So when Hiven Tampen is in production, Tampen will have a reduced emission of around 200,000 tons CO2 per year, which is equivalent to about 100,000 cars. And 3.5 million tons accumulated and 1,000 tons NOx per year. So that's a part of it, but then we should maybe focus even so much on the technology development part of it, because it is a further development of the Hiven floating wind concept with sized up turbines, and it is deeper water and it's more harsh environment. I noticed on the presentation you started off with that the floating wind was not defined as a mature technology, and it of course it is not. It is in development at the same time as we have already Hiven Scotland, which is 5 turbines on the Scottish sector that is currently producing. The Hiven Tampen will be the first floating offshore wind farm, though, to supply renewable power to offshore oil and gas installation. Hiven Scotland, it's supplying to the grid in the UK. And we will have a fully integrated wind turbine and gas turbine power generation system in an island mode, in a soft grid, which is very interesting in a global perspective. We are also aiming at reducing the cost of floating wind turbines. When we upscale the number from Hiven Scotland, the technology development and there's more efficient project execution, the construction methods, we aim to reduce the capex by up to 40–50% compared to the previous Hiven project. We also open up for Norwegian industry contribution in the floating offshore wind developments. And in the project of Hiven Tampen, we have up to 50% of Norwegian content on the contractors. So go a little bit back into why have we chosen the Hiven Tampen area. Well, I think the technical evaluation that was taking place, it was looking at the power demand. And Tampen with the Snorre and Gullfaks installation has a very high power demand. And with an early production of 360 to 400 gigawatt hour, we will cover about 35% of their total demand. Both of the fields, they have a significant rest life, and it is the potential for extension both for Gullfaks and Snorre. At this point, we have Gullfaks at 2034, whereas Snorre will live until 2040 at this point. Then the fields are also far from shore, about 140 kilometers. That means that the alternative electrification from shore is very expensive. And as such, the island mode concept of fully integrated wind power to an industrial facility is demonstrated. And this is very interesting in a global perspective, and by some of our partners, this was actually considered to be the most interesting technical element. The platform electrical system also on the platforms was suitable for connecting wind power, and the required topside modification were limited. It will only be required to have a cable tie-in to existing systems at Gullfaks, whereas a new transformer on Snorre will give a much higher power utilization, and it can be justified. So a bit more details to what the Hiven Tampen project is. It is a common wind park that is located halfway between Gullfaks and Snorre. The water depth is about, as I mentioned, down to 300 meters, and it is 5 turbines that is planned to go to Gullfaks, and there's 6 going to Snorre. And there is a total of 88 megawatt divided by these 11. There's about 14 kilometers in each direction, and we will cover an area of 20 square kilometers. And we have configured, as you see also from this sketch, that we have configured it in a ring, all the turbines in a ring, and that means that it increases the flexibility of the production and the technical availability. It's less sensitive towards any damages on cable and the inter-array cables in between the turbines. We will have different options. Also, it allows transfer of turbines between the licenses at a total higher utilization of the wind farm during the lifetime of the fields. This could be, for instance, during a maintenance period on one of the platform installation, it will be possible to reroute some of those turbines over to the other cluster. So to summarize, it's 11 turbines. It is a concrete substructure, steel tower and blades. It is kept on occasion by anchor chains that are connected to suction anchors. Some of them will support anchor chains for multiple turbines, up to 3 pulling in 3 directions. And the power will be transformed through about 15 kilometers cables up to Snorre and Gullfaks. So there has been a lot of focus on the support for Enova and also the technology development aspect of it as such. And to step back, what is the actual technology development from previous scale projects like Hiven Scotland? For a start, the turbines are bigger. The Hiven Scotland has a 6 megawatt turbine. The Tampen has now an 8 megawatt turbine, which is now rated to 8.6 megawatt, and we're looking at possible take that advantage into our total grid. The rotor diameter is 167 meters, and comparison to a football field, it is 100 meters. So it's quite large blades. And from blade tip to the above sea level is 190 meters. And for comparison, the Oslo Plaza, for those of you who know Oslo, is 117. Eiffel Tower, 324, so it's not as high as that, but it's quite large structures. And below sea level, as you see here, it says 100 is about 90 meters from the sea level and down to the spa substructure. Then on the construction side, that's also some advantages that we have been achieving. The assembly method that shall be used is based on an onshore crane. It's one of the largest in the world. Hiven Scotland were using the large crane on the Saipem 7000 vessel, and it is very expensive at the same time as it is also normally booked for the season at the time at a very strict schedule. So it allows us for more flexibility contractually, and it's also reducing cost. Then it is the anchors. We're having joint multiple anchors, shared anchors. We have been saving 14 anchors by having this combined utilization. I mentioned that the substructure is made of concrete. That in Hiven Scotland it was made of steel. Not only the material itself of concrete is cheaper, but also the fabrication, the vertical fabrication, and transport removes the need for the costly upending operation that we would have to have if it was a steel alternative, since they are transported horizontally. As you saw in the video, you were seeing how it is produced at the deepwater site. It is easier to fabricate locally, and especially if you have the right geographic conditions, as you have quite a few fjords in Norway with the deepwater sites. So then it is the integration to industrial that we see as quite a challenging task, to have the integration into the control SCADA system of the platforms. And I'll come a bit back to that. Just a few words on where we're at in the project. Where, as you understand, in the middle of execution now. We have set all the contracts. We did have the Prime Minister visiting us here at the offices of Fornebu in Oslo, where I'm sitting, delivering the PDO to her, and well, it's a year ago now. Then it has been a year now with the detailed design and the procurement and the preparation activities. And now we are standing before the fabrication. It did actually start the 2nd of October, I believe. Again, we had Anna Solberg visiting us together with other prime people, having the first steel cut at the Stord, where Kvarna has their facilities. So now we are started to build the substructures, and in 2022 it is the year for doing the assembly and the installation, completion, and then finally a startup that we aim and we hope for in the 4th quarter of 2022. So a few words on the operational part. We will have the control room for, it will be Equinor who is the operator, and we will have our control room at an existing control room, actually, combined with Valemon, for those of you who know that field, in Bergen, which is on the west coast of Norway. The operation could be kind of split into operation of the wind turbines itself and the platform, which will be a bit autonomous. The operation and maintenance of the turbine, for that there will be a service contract with Siemens Gamesa for a 5-year time before we take it over ourselves. And we will have a joint service with Equinor existing marine operations for the maintenance. Then it's the platform clusters of Snorre and Gullfaks. They are run.
Gertrud, now we cannot hear you anymore.
Turbines.
Okay, good. It's good.
Yeah?
Yeah, it was just 10 seconds.
Sorry?
It's all fine. It's all good. I think it's good now again.
Did you lose my?
Yeah, it was just for 10 seconds. Yeah.
Just tell me when I shall continue.
It's fine. You can go. I think you can go on. Just repeat maybe what you said in the last 5 to 10 seconds.
Oh, okay. Sorry. Yes, I just said that Equinor will be the operator, and we will have a combined operation with already existing activities, marine fleet that we have, taking care of the oil facilities in Western Norway. And then we will have the platform clusters of Snorre and Gullfaks. They have their operational autonomous, and what is the connection is, of course, that they will have the power management system taking the signals and input from the wind power forecasting through an energy forecasting system. There is no battery backup or power cable or anything like that. So the current energy supply is provided from the existing gas turbines at the various platforms. It is Snorre A and B and Gullfaks ABC. Thereby the power from the wind farm shall replace the supply from the gas turbines. And in order to do this, to put it simple, the gas turbine shall be turned off when wind supply is good and started up when weather forecast is low. It's so easy and so quite complex. The operation of the G2Gs to ensure stable power generation is a part of the platform's daily work, and we will assume having a conservative spinning reserve the first couple of years, running the G2Gs, perhaps one extra or on a low on a low megawatt to keep it prepared in case that there arises any issues that we are not prepared for. So the first, say, 6 months, we're expecting to run on a relatively high spinning reserve until the platform and the operators get more familiar with the systems. So just a little bit back to how we started up. What does the future look like? Equinor is aiming to step up on floating wind so it becomes a competitive source of energy. At this point, it is not. We have the support from Enova in order to get up to an NPV of 0. So the technology development has been taking place, and quite a few technology gaps have been reduced for each project, going from the demo project on the 2.3 megawatts to Hiven Scotland and now Hiven Tampen. But as part of this travel, we have reduced the cost per megawatt for each project, and we aim to reduce even further to get the future development. And we see our future project to grow above 500 megawatts until we have an industrial source of power that is competitive. Equinor is looking at potential for floating offshore wind project both in Norway and the UK, in Europe and US and Asia. Now the most very interesting, of course, is that the new areas of offshore wind in Norway that has been launched, which is the Utsira Nord. That's an area that is exceeding the water depth of, say, 100 meters. That maybe is the maximum for, that you need to have a floating wind. So we're hoping that that will be our next big project. And our long-term vision for offshore wind in Norway. Well, this visionary plot you see is a time schedule and the installed offshore wind capacity in Norway. EU reports are based on the large areas are developed in the North Sea and supplying oil and gas or other power-intensive industry. At higher capacity and power supply to Europe, or a future new power demand in Norway, ammonia, hydrogen for green shipping, batteries even. We do, however, need to get costs down per megawatt to become a sustainable power supply alternative. And this is where Hiven Tampen development now is the next step, and Equinor is hoping to realize a major floating offshore wind projects in the future. Thank you.
Yes, thanks a lot, Gertrud. Very interesting presentation. We got also already some questions, but we will address all the questions in the end. The questions can be asked in the question panel. And then I head over to the next presentation to Martin Vanetste. So while I'm introducing you, you can already fix up your screen and share the screen. So Martin, following a PhD at the University of Ghent in Belgium and a postdoc at the University of Tromsø in Norway, Martin started working as a principal geoscientist at the Norwegian Geotechnical Institute in Oslo. His research interests largely focus on the geophysical methods for site characterization, geohazard and risk assessment, and multidisciplinary data integration. In the last few years, his work has a particular focus on the development of data-driven ground models for offshore renewables, or group of geophysicists, geologists, and geotechnical engineers. Martin is currently heading the Offshore Geohazards and Geodynamics section at NGA in Oslo. Okay, the stage is yours, Martin.
Thank you. Can you see the screen?
Yes, we see.
Okay. Thanks for the introduction and inviting us to be present on this rather interesting series of workshops. So here I will present the current status of what we call data-driven geosolutions for offshore wind projects. And as the topic was clearly about the integration of the different disciplines, we'll talk a bit about geophysics, geology, and geotechnical engineering data and how we can try to match that and fit together in engineering design applications. So the outline, I'll briefly introduce the challenges that we have. In other words, what are the opportunities that we have and the charm of the subsurface complexity. Then I'll say something about the ground models, and it's important to understand what are the methods that we are using, what are the advantages and the disadvantages of those, before we look into a number of applications towards the data-driven quantitative geosolutions. And at the end, I'll present a little looking ahead what we can do maybe better in the future. So the challenge is very often that you have an offshore wind lease, and you collect some bathymetry data. There's very little uncertainty related to the bathymetry data, typically very high quality data. And then you often shoot a fairly poorly coverage of 2D seismic data in the area. The next survey typically collects a number of isolated CP2 in situ testing, geotechnical testing profiles across the area. But then what we often realize is, as this is early phase, there's a number of developments, there's a number of iterations. Often the grid layout needs to be optimized, needs to be changed. There's maybe new developments, bigger wind farms, maybe we need more space between the turbine locations, and there's a lot of iterations in order to fit the data best. So often the situation is that you have an incomplete data set, there's multiple surveys that are taking place, and you have different levels of resolution and coverage of the data. The trend is, however, towards much more fast-track projects. There's cost efficiency that is required. We try maybe to reduce the number of surveys that we have, and there's a tendency of having much earlier decision-making in most of these projects. So the main question there is, how can we really maximize all the data that we have into a consistent framework? And according to us, this is basically related to the ground model. And what you see here is the charm. This is not necessarily the North Sea, but this is an offshore wind farm development in international waters. What you see there is the top several tens of meters of subsurface. And you see that the subsurface is rather complex. There's a lot of glacial processes, a lot of very interacting features that you see there. So there's an enormous spatial variability of your soil conditions. So how can we really capture that in a consistent ground model that the engineers can use? So for us, it's about the ground model, which is per definition a 3D representation of the Earth's surface and the subsurface based on any valid data input, and that is an ISO definition. So this essentially entails that the ground model would provide you the spatial 3D understanding and a summary of the static and active conditions of the site. It should be updated whenever you have more data that becomes available, and it is actually used as a decision-making tool for geohazard and risk assessment, optimizing the data acquisition, changing the layout plans, and specific foundation designs. But what we see when we look at the current status of the ground models, very often the bulk of the data is the seismoacoustic data, which have maybe not a direct link to the geotechnical data that are used by the end users. We see that the ground models are often more qualitative than quantitative, and uncertainty is not very often presented, and also the ground model as such is not really used in engineering design because we typically don't present the right parameters in the right framework. What can we do to make that better? We need to understand all these different building blocks that we have, essentially the geophysical, the geotechnical, and the geological data. All of these data, they are very powerful, it's very complementary techniques, and we need to take the best out of it. None of these data is perfect. We all use our own language, and we need to communicate better what we can do. But it's really about the integration of all these techniques that we can move forwards. When we look at the geophysical data, we know that these are non-invasive techniques. We have 2D often for the offshore wind farms, sometimes 3D data, not very often, but we have typically millions of traces. It's often the seismoacoustic type of geophysical data that we use, not complementary data. The drawbacks of the seismics, particularly in shallow water, is the presence of very strong multiples that hamper the interpretation of the data. We struggle a bit with time and depth conversions. It's very difficult to explain an engineer that we work in time, but they need it in depth. And we have also some ghost issues that need to be processed out of the data in order to increase the resolution of the data. The resolution for the offshore wind farms, we go down typically to, let's say, meter scale resolution, but we lose resolution with depth. And the parameters that we have are small strain parameters. It's the reflectivity, it's the acoustic impedance, it's the P-wave velocity, maybe some attenuation or a Q factor, it's maybe a density and maybe a Poisson ratio. When we look at the geotechnical data, what the engineers typically would be using, these are invasive techniques. They are essentially 1D, and if we're lucky, we have a few tens of data. There is a tendency of collecting more data, but in essence, it tends to maybe 100 data across a wind farm zone. They combine the CPT data, so the cone penetration testing data, with samples. We do get a resolution in the order of centimeters with these data, but what we see afterwards is that we use a lot of empirical relationships between the measured parameters and the engineering parameters that are required. What we also see is that when we get a sample from the subsurface, it is typically deformed, and sometimes the sample quality can be poor. So we have to reflect on that when we interpret the data. And the parameters that the engineers would be using, it's essentially large strain parameters. It's the undrained shear strength, it's a weight, it's a friction angle, it's a shear modulus, a void ratio, a density, and a large strain Poisson ratio. The third bullet here that we have, it is geology. This is basically covering all the processes by which the soils form and change over time. It is really essential. It is often a qualitative branch of activities, but it's extremely important to put everything into the right time and spatial scales. We talk with geology very often over really large-scale processes. It's covering, as you see on the map over there, it's covering big areas. We have seen on the seismic data before, we see clearly the glacial imprints on the seismic data from the glacial processes. If we don't understand the geological processes, it will be difficult to come up with proper geotechnical parameters and understand what they behave or how they behave. And as well, for the geophysical data, we need to understand the geology to understand the geophysical data. And the drawback is maybe that in some cases you may have some geofantasies. When we look at an example here, this is the typical 1D geotechnical data that one would have. You have on the left-hand side a tip resistance from the CPT, and the middle panel is the pore pressure response. The right-hand side is the converted undrained shear strength. For a site 25 meters deep, give or take, this is a normally consolidated site. This is the Finnegefjord area. You see some spikes, you see some variation in the sedimentary response. And at depth, the main features that one would see is these negative spikes on the pore pressure, which are sand layers that you see. Otherwise, you may not see things that are very distinct. When we look at multi-sensor core logging results from the same site, then we get geological information. Here we have a much higher resolution even on the density and the magnetic susceptibility. And we start seeing that we have quite a peculiar reflection at maybe 3 meters subsurface. There's something quite peculiar over there that stands out more on these data than on the geotechnical data. But again, this is 1D. We can do the same thing with the seismic data. This is a 1D trace. On the right-hand side, the gray trace, this is from an ultra-high resolution 3D seismic cube in the area. And then as we have density and acoustic velocities from the multi-sensor core logging, we can calculate a synthetic signature as well. And we see actually quite a distinct reflection over here as well. We have to put that into the bigger picture. And this is a seismic profile. It's one of the inlines of the ultra high resolution 3D seismic data. We looked at the trace from this Calypso core location. And what we see there is actually a slip plane of a submarine landslide. What we did not easily identify, we see an anomaly, a small anomaly on the geotechnical data, but it's much clearer on the geophysical data and on the geological data. But here as well, you see again, we need to look at the bigger picture because your core that you have been taken here, if you only use that in your design, the results from that core, you will probably miss quite a bit of the subsurface. You will not characterize that properly as there's so many spatial variability that we have to address in our models. So how we do the quantitative ground model, we look at the data, we have to look at the multipurpose data integration. That means that we have the CPT data, which is actually the driving force. It's these parameters that our engineers are needing, but we have a bulk of geophysical data. We have to integrate that together. We have to basically come up with a 3D prediction of geotechnical parameters. And at the same time, we have to present an uncertainty on this assessment. And then ultimately, we hope that you can maybe use that to design your engineering or your foundation concepts that you have in mind. So I'll show you a few examples of what we can do. It's important to make the difference between the qualitative and the quantitative ground models. When we look at qualitative ground models, these, for me, that would be more geological models, where you look, okay, maybe there's a landslide deposits, you describe the features, you have a reasonably good understanding of the geological setting, but you do not necessarily come up with a detailed geotechnical imprint of the properties at that site. And often you would present that in an overlay, you have your sedimentary facies, you look at the CPT on top of it, but that's the level of integration that you have. But we do move forwards towards the quantitative ground models, and I'm going to show you a few examples of those. What we realize over there is that there's much more benefit to gain from the geophysical data if we really look into a bit more detail and if we link properly with the geotechnical engineers and the geologists for these things. We do realize as well that the level of maturity is lower the more we go to the right here, but the level of complexity and the level of integration is actually getting much broader. And I think this is the way we have to move forwards with all these type of analysis, getting more of the data, using it more in an integrated approach. So the easiest way, what we would do is we look at the CPT, so a cone penetration test result at a given site. You have the tip resistance, also model parameters versus depth, here the top 50 meters. You sit together with the geotechnical engineers and the geophysicists and the geologists. What the geotechnical engineers would be doing is they typically divide the areas of where they have a significant change in the CPT response. That makes sense. We do the same thing over the geophysical data. But the main part here is that we have to identify where these horizons match. It's very important that we capture the subtle changes in the geotechnical data, but in a consistent way with the geophysical data, because if you start interpolating, we only have the geophysical data to rely on. So what we have to do here, we have to match the different horizons that you can see in the geotechnical data with the geophysical data and come up with a consistent interpretation in depth. An easy thing to understand is that you do then trendline fitting on each of these units. So this is a top-down approach. You have your geotechnical units, they match with the geophysical data. You do a regression analysis in each of these units. With a regression analysis, if you do that in a robust way, you can come up with standard deviations on this. We know that these geotechnical properties change approximately linear within these units, so that is quite okay. And then what you can do, you start using the structural framework that you get from your seismic data, and you calculate a gradient and an intercept of each of these parameters that you are interested in for each of these units. What you then do is basically you stack it again, you go from top to bottom, you take the intercept and the gradients, and you reconstruct your geotechnical profile from these data. This is a model that is quite easy to understand. It works reasonably fine, but it does depend on the resolution of your data and the interpretation that you do on the data. So there is a certain bias related to this work. If you have a very complicated site, it can take quite a bit of work to do that as well. But there's a number of advantages. If you don't use the geophysical data, for example, you will not necessarily understand why some units are disappearing in areas, you have truncations, you have channel formations. You have to make sure that you capture all the geological features in the best way and match the units in the systematic way as well. The next approach that you can do is going a little bit more detail. This is aside from the Dutch area, the Dutch wind farm area. What you see is the seismic profile on the left-hand side, a number of CPT profiles as these cones. And then on the right-hand side, we have predicted the tip resistance from the CPT data using not only the stratigraphy that we see, but also the seismic velocities. So we basically develop a co-kriging method where we take the advantage of the variance between different variables that we have. And this is particularly appropriate when we know that the main attribute of interest, which is the CPT data, is actually quite sparse. But on the other side, we have really a lot of secondary data, which is the seismic data. And in this side, we realized that there was a certain relationship between P-wave velocity and the tip resistance that we had, which is not necessarily the case for all areas. But we tried that. You can come up with a reasonably good understanding of the predictions. We have done a blind test on these data. We get a reasonably good approximation of the predictions when we compare that with the measured data. It is maybe not perfect, but it's a model of good resolution and a reasonably valid result that we get out of it. And at the same time, as you do a co-kriging approach, it also allows you to assess some spatial variability and a standard deviation on the results, so you can address uncertainty that you have with your data. Then there's even a next level. Why don't we try to do what is basically happening in the reservoir geophysics? You can start working on machine learning approaches and also using acoustic impedance inversion, for example. This is a field of development. It is possible. The seismic profile that you see here has been successfully converted into an acoustic impedance result, and this is still very high resolution. We still talk about the top 50 meters of the, or maybe less, maybe 30 meters of the subsurface. So we have methods available to map the seismic data into acoustic impedance. There is, of course, a number of empirical relationships or soil physical models that we use for that. But also, if you do that in a genetic algorithm or a stochastic approach, you can come up with confidence intervals to get at least a level of uncertainty. We know it's not perfectly right, but at least you get an estimate of what the acoustic impedance could be with a range of uncertainty on it. The next step is then again, how do we remap these properties into what the geotechnical engineers are needing? As I said before, it's the underhand shear strength, it's maybe Gmax, it's properties like that. And they are not always straightforwardly linked to the propagation of the seismic wave fields. If you look at two examples, we have on the left-hand side, the same site, which is Finnatefjord. On the right-hand side, we have a wind farm development in the Irish Sea. This is the example that I showed before as well. You see that the seismic data is obviously very different. And what we have done in the middle panel is basically mapping the measured QT from, so that is the tip resistance from the CPT data, with the acoustic impedance that we do from the acoustic impedance inversion algorithm. On the left-hand side, we get a fairly good linear profile over there. On the right-hand side, for the Irish Sea, we clearly see that there's not really a very proper relationship. So in this case, we see that the relationship between the compressional wave properties and the geotechnical properties is apparently more complex between these two sites, and it's clearly not a linear function that we have. And we realize that these impressions you will get, it's clearly indicating that there's a variability from site to site, but also from the different phases that you will have. You see that the different phases that you see on the seismic data, they probably match or map out in different areas of this QT versus acoustic impedance plot. So then this is typically a type of approach where machine learning can be quite functional, because machine learning is exactly trying to find relationships between properties where you do not easily find relationships yourself. So and if you do that, we can now look what is the measured QT versus the predicted QT, and then you can line up these things quite well. So there is certainly a power with using machine learning if you want to match the geotechnical and the geophysical data in a more consistent way, even though this is quite a time-consuming procedure. This is an application on the Dutch wind farm where we did the same approach. This is a CPT profile that we have. With the black line is what is measured. What we have with the green line is using the machine learning approach and the neural network, the genetic algorithm and the artificial neural network in an approach to map the CPT response. So here we use it as part of the training set. And then the orange line is removing it and doing then the blind test. So we do see that we have actually a quite good prediction of the CPT from the geophysical data in that site. Again, I have to stress this is quite a tedious exercise. It's a lot of computational time that you need to successfully achieve that. But using multi-attribute regression analysis, and the parameters that we use here were envelope trace amplitudes, it's acoustic impedance, it's the attenuation or the quality factor, it's the stratigraphy, and it's the measured QC. We see that we can be able to predict or to map the geophysical data and the geotechnical data to quite a high precision. So where does that lead us? As we, although all of these methods are somehow stochastic or take into account spatial variability, you can basically try identifying areas where your models would predict that you have less control. This is a map where we have the normalized standard deviation of the predicted QC parameter over wind farm development. And over there, we can clearly see that there's the red zones where if you go back for a targeted site investigation, you can really pinpoint areas where the models predict that you have a big uncertainty. So these would be the areas that you go back. You can basically update your models on the fly and get an updated assessment to tune the upcoming site investigation even better. Then the same thing, once you get there, you can basically create a 3D cube of geotechnical properties. Here, this is a model of an undisclosed area where we have mapped 3D the QC properties across the entire site. And then you can basically load that with your seismic data in whatever 3D seismic data interpretation software. So we start bridging the gap between the geophysical data and the predictions that we have, and you can do the same with the uncertainty. So this is, I think, a big step forward to understand what is happening in your area and map the data for the geotechnical engineers so they look much more into spatial variability, as we have seen that from the geophysical data. Then you can even push that further. There's very often very specific models that people are using in order to come with geotechnical engineering design. So, for example, what we have tried to do here is we use a model to obtain a capacity that you need to calculate optimal diameters for example, a monopile design. I can't explain you the details. That's where your engineers come and help you out. But over there, what you basically need to do is you need to get an estimate of certain soil parameters that you then put into a model. What we can do with these ground models is, as we have now mapped, this is the same area as I showed before, as we have now mapped these properties over a 3D area, and we have the information from the properties and the uncertainty, then we can come up with basically finding out what would be optimal pile geometry, and then you can translate that actually in a cost function, because the diameter and the pile length determine the amount of steel that you would need. So basically you can start using this quantitative ground model from a fairly low number of CPT data, 23 CPT data sets in that area, but a bulk of geophysical data into a much more detailed picture. So what you would see, for example, on these maps is that the area to the left seems to be more competent, where you may need only a thinner pile diameter and basically shorter piles. So if you can do that in more detail and use maybe more advanced approach, you can come up with a much better understanding and constraint of your geotechnical engineering design that you can do. Then if you look forward, and I think Benjamin is quite happy that I show you this slide because it's basically one of his. What you can see here is that very often we use these models based on 2D seismic data, but ideally we'd like to use the 3D seismic data. It gets you away from quite a bit of uncertainty, because whatever you do with 2D data, you still have to fill the gaps between the seismic lines. Very often with offshore wind farms, the spacing between the lines is still in the order of 100 or maybe a few hundreds of meters. So you introduce quite a bit of uncertainty. You can do geostatistical approaches, but if you collect the 3D data for starters, it's of course getting much better. And then the advantage what you have on top of it is you can make all these time slices, as you can see here. This is not the seafloor topography, but this is a subsurface geomorphological image that you have from this area in the Barents Sea. And then you can start doing all these advanced interpretations and really get into a much better 3D picture of the subsurface, linking that with the geotechnical data as well. And also, basically, so far, we typically use Pwave data. It's more of a challenge to use, for example, shear wave data, but what you see on the left-hand side, this is actually a result where we have tried to combine sonic scanner results with CPT data from a shallow oil and gas field. Over there, with the sonic scanner results, you basically get also, next to the P-wave velocities or the slowness, you can also get the shear wave velocity. And we have done some correlations, basically linking the geotechnical and the geophysical data here, looking into what you have for the P waves. That would be the triangles that basically line up on this vertical line here. So there's no relationship with P wave slowness and underhand shear strength. However, if you look at the shear wave slowness and the underhand shear strength, then you see that there is quite a decent change. So they are much better correlated. So we should try to use much more effort in using shear wave velocities for our site characterization. And there's more of the geotechnical parameters that relate to shear wave velocities than to P wave velocities. A lot of the earthquake engineering that one would do, and one would do that for offshore wind farms as well, requires, for example, parameters also as the stiffness. This is directly related to shear wave velocities. So if we move forward, ideally we'd like to have much more shear wave information collected or extracted from the data at the same time that we do P-wave analysis. In order to sum up, we can work on quantitative grant models. These are actually models where we use a collection of multidisciplinary quantitative data, and we try to use the benefits of all of these data, and they're all very important. There's not one that is more important than the other one. It's geology, it's geophysics, it's geotechnical engineering. We try to use the seismic data to integrate with the geotechnical boreholes to really populate the 3D volumes with geotechnical parameters. And it's important that we then come up with a geologically consistent framework. Very often we would see that geotechnical properties may be similar, but the geology will tell you that they are fundamentally different units, even though the shear strength behavior may be similar. But the geology will tell you if it's really a fundamentally different unit, you have to describe it also geotechnically in a different way. What is also important that these models, they should evaluate uncertainties essentially throughout the entire workflow. And there's uncertainties in a lot of things that we are doing, but we have to capture that better. It is important to address that when we do the acquisition, the foundation design, and the hazard and the risk assessment. It is important that these models, they are driven by the data now, not just by assumptions. Ideally, the future will also tell us that we can use complementary data and maybe start using machine learning approaches, combining data from other developments into new developments. And I think we have a number of cases where we see that there's a lot of promise in these data, in these methods. But I think it's also fair to say that it's early days. We need more data, we need more cases, and we probably need to test out different machine learning approaches to really make the approach even more consistent and acceptable. And that is my last slide. It's actually all about the geo community that we are using. We develop many things, but we need, as I said, geotechnical engineers, we need seismic data experts, we need the geologists, we need people who are good in data science, we need people who can look in inversions. We need basically to sit together, work together, and make sure that we deliver the best possible products for everything that we are doing. And that can only be by working closely together, which is, I think, the main message here. Work together and communicate together. Thank you.
Thank you, Morten. Very nice presentation and very nice message to all of the geoscience community. So we got some questions coming in. Before I forgot to in the chat, I forgot to forward you. Paula did that, but I will share the link again. We have a short survey that you could fill out for us. It's just 3 very short questions on. I shared the link again in the chat on about your background. So we are of course interested in who is following this event. So if you would like, you could open that link, and we would very much appreciate if you could fill out so that we know a bit more about our community. Okay, but then we got some questions, especially as Christian Otterbein has a lot of questions. Would you like to speak up yourself, or because it's 3 questions, so I can, if you want to address it yourself, you can do that. Otherwise, I will select 1 or 2 of them. Christian? Okay. Yeah, in that case, then I start. So it's questions to probably addressing more the first talk of Gertrud. So Christian is wondering what consumes so much power on a platform that the wind park only covers about 35% of that energy need, and how is that power currently being produced? Did you hear that, Gertrud?
Yeah, well, I think maybe it's twofold. I don't think I can refer to what exactly. Remember, this is there are 2 platforms, Gullfaks A and C, and then there is also Snorre A and B. So we are talking about 4 platforms here. It's not only 1. I cannot speak for all the demand sources on those platforms, of course, but it is gas turbines and steam turbines on the Snorre B that is providing the power as of today. And then when we have the 88 megawatt online, it is of course possible to see that we could use everything all the time, but we need to have some backup, is what we call spinning reserve. So to start to replace 100% of the power with wind power is not something that we can take the chance of due to the risk of shutdown. We need to have a certain backup. So I think that 35% is what we aim for now to start with. And in order to reflect exactly which demand all the components that we have on the platforms, I cannot answer.
Okay, yes, then I guess this goes into a similar setting, and I'm not sure if Martin also wants to comment on it, but first of all, it's again a question to Gertrud. It's about monitoring. So how do those wind installations impact the seismic surveys and monitoring, as obstructions creating holes in seismic coverage, as well as seismic signal reflectors and noise generators? Do you have any
difficult questions. You mean seismic in the area? It's not seismic exactly in the area where there are running seismic surveys along the park for Visund, but that is only campaigns, so it's no permanent seismic net, if that's what was the question.
Yeah, maybe it will also go into more 4D surveying of current installations, if it's anything going on that. I'm not completely sure how if that was part of the question as well. So.
Well, it is in the middle. It's quite a far distance from Snorre and Gullfaks installations after all. Also, we have the installation of Visund that is laying a bit northeast. And there will be some campaigns running for that seismic just a few years, I believe, after that we have started. But we don't expect that to have any impact, no.
Okay. So if in general, if anybody wants to speak up, you can also now unmute yourself and ask questions yourself. I want to give also other people to ask questions. Also, any questions to Martin or so, you could speak up now. If someone has something to ask, I'm sure they're both happy to answer. Everybody happy, tired, or whatever. So then, okay, I got the last question, and or Carla, you have a question? I saw that.
No, sorry for introducing. Sorry for yeah. No, I just wanted to say that we have a survey to share with you. So I think, Benjamin, you sent this link already.
Mm-hmm.
But I'm gonna send it again. So if you have a moment, please, could you just fill this survey we are sharing with you? And yeah, sorry, this is everything I wanted to say.
No questions on that way. Okay, then we have a last question, and that goes is a bit about the energy balance on this Tampen Hiven. I guess it's again, yeah. So it's what is the current energy balance in terms of energy gained in form of hydrocarbons by the platform system versus energy consumed by the platform system without any wind? What is you have any information on that?
I didn't quite. Can you just repeat the question?
Of course, I can repeat the question. So the question is, what is the current energy balance in terms of energy gained in the form of hydrocarbons by the platform system versus energy consumed by the platform system?
I don't know. I have to come back on that.
Okay, so maybe it's Christian, if you want more detailed answer, I guess it's best if you email Gertrud directly, and she can probably forward you to the people who know about it.
Sure, that's I will do.
Great. Now, okay, I don't see any more questions, and we're anyway over time. So thanks a lot to both of you for the presentation. Really great presentations, and we really look forward to hear more on wind power and characterization of shallow subsurface. So big thanks to both of you, and all the best in your future.
And to you.
Thank you.
Thank you.
Thank you.
Yeah. Good.